Hello everyone, this is Jisoo. My metric number is 22110573. My presentation is titled Inventory Policy Evaluation Under Demand Uncertainty, a backtesting study using real demand-supply balancing data. This project was conducted for the Master of Applied Statistics Industrial Statistical Project using real company planning data from SWAP Asia. The main aim of the project is to evaluate how inventory policies perform when demand is uncertain. In particular, the project looks at whether the current planning baseline should be retained, adjusted, or supported by a statistical inventory policy. The analysis is based on clean DSB data covering 356 SKUs, 7,357 SKU week observations, and an estimated gross margin of about 164.9 million ringgit. So the project is not based on a small artificial dataset, but on actual operational planning records. This slide shows the roadmap for the presentation. I'll begin with the project context and the business problem. Then I will explain the analytical framework and the statistical design used in the project. After that, I will describe how the raw DSP fields were cleaned and how ethnical data boundaries were handled. The main part of the presentation will focus on the findings, especially demand uncertainty, forecast accuracy, inventory position, and policy backtesting results. Finally, I will present the recommendations, reflect on how the project relates to the Master of Applied Statistics program, and close with the main conclusion. The structure follows the full statistical project logic, from a business question to analytical evidence and then to practical recommendations. This project is an application of statistics inside an actual organizational planning process. It is not only a technical exercise where I apply formulas to a dataset. Instead, the project uses statistical thinking to review a real demand supply balancing or DSB planning system. There are four ways in which the project applies statistics. First, it has a statistical consulting element because it translates business risk into measurable outcomes such as fill rate, stock out rate, holding cost, and total inventory related cost. Second, it is organizational statistical problem solving because the project addresses a real inventory planning issue under demand uncertainty. Third, it creates a new analytical system by transforming weekly planning fields into reusable evidence panels. Finally, it reviews the existing DSB planning system by comparing the observed current planning baseline against alternative statistical inventory policies. The strongest emphasis is on organizational problem solving and review of the existing planning process. Swipe Asia operates in the mobile device lifecycle and supply chain service industry. In this type of business, inventory is very important because products availability directly supports fulfillment, channel programs, and service continuity. At the same time, mobile device can become costly to hold because models change quickly, price may fall, and customer demand can shift across brands and product generations. This creates a clear service cost tension. On one side, if the company holds too little stock, it may face stockouts, loss margin, and service issue. On the other hand, if it holds too much stock, inventory may tie up working capital and expose the company to overstock or obsolescence risk. So, the inventory planning problem is not simply about keeping more or less stock. The key question is how to balance product availability with inventory cost in a changing demand environment. The main research question is which inventory policy achieves the most appropriate balance between stock out cost and overstock cost under demand uncertainty. This question turns a practical planning problem into a testable statistical comparison. To answer it, the project had five main objectives. First, the raw DSB snapshots need to be cleaned and transformed into structured analytical dataset. Second, demand uncertainty and forecast accuracy need to be measured. Third, inventory position and replenishment indicators need to be evaluated. Fourth, the observed current planning baseline and several alternative inventory policies need to be backtested under the same historical demand environment. Finally, the project should provide practical planning recommendations for SWAP Asia. This is important because the DSP file shows the planning situation at the one point in time, but it does not directly show whether another policy would have performed better. Backtesting is used to make that comparison possible. This project used company operational data, so ethical handling of data was important. The data was used only for academic project purpose. Company operational information was treated as confidential and no customer-level personal data was used in the analysis. The results were reported at an aggregated SKU and policy level rather than exposing sensitive transaction-level details. There were also important boundaries in interpretation. Actual sales were used as an observed demand proxy, but actual sales are not always the same as true unconstrained market demand. For example, if a stock out occurred, actual sales might understate what demands could have been. Also, the project does not claim to be a complete inventory transaction ledger simulation. True lost sales, customer back orders, exact receipt timing, and full stock movements records were not fully available. Because of this, the analysis is based on transparent planning position, praxis, and clearly stated assumptions. This slide summarizes the analytical framework of the project. The process begins with the raw DSP Excel snapshots. These files are then cleaned and structured into analytical panels. After that, the project examines demand, patterns, and forecast accuracy. This is followed by inventory position and replenishment analysis, because the project needs to understand not only demand, but also how stock, purchase orders, and planned orders appear in the company's planning view. Then, alternative inventory policies are designed. These policies are tested using a train test backtesting framework. The final stage is service cost trade-off evaluation, where fail rate, stock out rate, average policy position, stock out cost, holding cost, and total cost are compared. So, the framework connects data cleaning, diagnosis, policy design, backtesting, and managerial recommendations into one project flow. The raw data consisted of 23 weekly DSP Excel snapshots, covering the period from September 2024 to February 2025. These fields contained SKU level information such as actual sales, forecasts, stock on hand, weeks of cover, purchase orders, planned orders, and products price field. However, the raw DSP fields were not ready to use statistical dataset. They were planning templates. Weekly values are stored across columns, and each SKU appeared across multiple raw types, such as actuals, forecast, warehouse stock, purchase orders, planned orders, and weeks of cover. This means that the first major task was data restructuring. The data had to be reshaped from a spreadsheet planning format into a panel dataset suitable for pattern analysis. One important data issue was that the weekly DSP snapshots dated 23 December 2024 was unavailable. This missing snapshot was not inputted because creating an artificial planning snapshot would introduce a planning view that was not actually observed in the company records. After cleaning, the final dataset supported both SKU week analysis and planning snapshots analysis. The cleaned evaluation panel contained 356 SKUs, 29 weekly periods, and 7,357 SKU weekly observations. Across these observations, there were 494,585 actual units and about 194.9 million ringgit in estimated gross margin. The main unit of analysis was the SKU week. This means each observation represents one SKU in 1 week. There were also planning snapshots records, which allow the project to examine forecast horizons, stock on hands, purchase orders, planned orders, and weeks of cover. The core cleaned panels includes the actual sales panel, planning snapshots panel, forecast accuracy panel, and evaluation panel. This clean dataset is the foundation of the project, but it's allow demand forecast, inventory position, and policy performance to be compared consistently. For the policy evaluation, I use the train test backtesting design. The purpose of this design is to avoid look-ahead bias. In other words, the statistical policy parameters should be estimated only from past data, not from future test period information. The training period covered observations up to 30 December 2024. The test period covered 6 January 2025 to 17 February 2025. Each policy was evaluated on the same historical demand environment in the test period. This makes the comparison fair because differences in performance are due to the policy logic, not due to different test observations. The mean evaluation measures were shortage, excess, holding cost, stockouts cost, and total cost. Shortage is calculated as the positive differences between actual demand and policy position. Excess is calculated as the positive difference between policy position and actual demand. This gives a practical way to compare inventory policies and their historical demand uncertainty. The project compared five policies. Policy 0 is the observed current planning baseline. It is calculated as warehouse stock on hands plus purchase order quantity based on the Horizon 0 BSB planning view. This is an important boundary. Policy 0 is not a reconstructed true inventory ledger. It is planning position proxy based on the available DSB fields. Policy A is an uniform service level policy. It applies a 95% service level to all SKUs. Policy B is an ABC based service level policy. A class SKUs receive a higher service level, B class SKU receive a moderate service level, and C class SKUs receive a lower service level. Policy C is a SKU specific safety stock policy. It adjusts protection based on demand variability, margin rate, and average demand. This is the best statistical alternative in the results. Policy D is a news vendor inspired policy, where inventory position is linked to underreach and overreach cost logic. Together, these policies represent different levels of planning sophistication. The first major finding is that demand uncertainty is structural. It is not only a forecasting issue. The average SKU week sales quantity was 67.23 units, but the median was only 9 units. This large gap shows that the demand distribution is highly skewed. Also, 23.69% of SKU week observations recorded zero demand. This means many SKUs were slow moving, intermittent, or had irregular sales pattern. The chart shows that many observations are concentrated at low demand quantities, while a smaller number of high demand observations pull the average upward. The implication is important. A single inventory rule is unlikely to work well across the whole product portfolio. A policy that is suitable for a fast-moving SKU may be too aggressive or too costly for a low-moving SKU. The second major finding is that forecast risk increase as the planning horizon becomes longer. The overall WMAPE was 38.27%, which indicates a meaningful level of forecast uncertainty. At Horizon 0, WMAPE was 31.18%. By Horizon 13, it's increased it to 48.09%. This means that forecasts may further into the future were less accurate than near-term forecasts. Another important point is that the forecast errors were not only one-sided, both under-forecasting and over-forecasting occurred. So, the company faces both stock-out risk and overstock risk. The practical implication is that forecast accuracy should be monitored by Horizon. It is not enough to look only at the one overall forecast accuracy number. The next finding is that gross margin contribution is highly concentrated across SKUs. The ABC classification showed that A-class SKUs accounted for 71 SKUs, which is about 19.94% of all SKUs. However, these A-class SKUs contributed 79.7% of total gross margin. The A and B classes together includes 162 SKUs and contributed about 95% of total gross margin. This supports differentiated service protection. A stockout for a high margin, high contribution SKU has a larger business impact than a stockout for a low contribution SKU. Therefore, it may not be efficient to apply the same service level to every SKU. Higher contribution SKUs may justify stronger protection, while lower contribution SKUs may require tighter inventory control. This slide focuses on inventory position. At horizon 0, the warehouse-only stockout risk proxy was 6.9%, but when purchase orders were included in the committed planning position proxy, the risk fell to 0.8%. This shows that purchase orders materially change the measured shortage exposure in the planning view. However, the interpretation must be careful. Warehouse, stock, purchase orders, and planning orders are not the same thing. Warehouse stock represent physical inventory. Purchase orders represent more committed incoming supply. Planned orders may still represent proposed actions rather than confirmed available stock. This is why the project recommends separating these categories in planning reports. Combining them too casually can make the planning position look safer than it actually is. The policy backtesting results show that Policy Zero has the lowest baseline total cost, but also the highest planning position. Policy Zero achieved a fill rate proxy of 99.71%, a stockout rate of only 0.97%, an average planning position of 471.93 units, and a total inventory-related cost of 5.04 million ringgit under the baseline cost assumptions. This means the observed current planning baseline is strongly service protective. Among the alternative statistical policies, Policy C performed the best. It achieved a fail rate proxy of 83.09% and a total cost of 10.9 million ringgit. However, Policy C still didn't outperform Policy Zero. This is an important result. It suggests that the current planning process contains useful operational judgment and service protection that simple statistical policies do not fully capture. This slide visualizes the service cost trade-off. Policy Zero sits as the high service, high position end. It gives the strongest service protection, but it also requires the highest average planning position. Policy D has the lowest average position, but it creates the highest shortage exposure and the weakest fail rate. This shows the risk of reducing inventory too aggressively. Policy C is the most balanced statistical alternative. It performed better than Policy A, B, and D among the statistical policies, but it does not outperform Policy Zero. So, the main conclusion is not that the current planning baseline should be replaced directly. Instead, the better recommendation is targeted review, not direct replace. Statistical policy logic should support planners by identifying SKU where current planning positions may be too high or too low. The sensitivity analysis tests whether the mean conclusion depends too heavily on one set of cost assumptions. The result is that Policy Zero was the lowest cost option in 8 out of 9 tested cost scenarios. Policy D became the lowest cost option only in one specific case, when the annual holding rate was high and the stockout cost multiplier was low. This scenario places much more weight on reducing inventory than on protecting service. So, the main conclusion is broadly supported, but it still needs to be interpreted within the limits of the data. There are several boundaries. Actual sales were used as observed demand proxy. True loss sales and customer back orders were not available. A full inventory transaction ledger was not available, and the 23rd December 2024 DSV snapshot was unavailable and was not inputted. Also, the test period was relatively short. Because of these limitations, the findings should be treated as proxy-based evidence for decision support, not as a perfect simulation of the company's full inventory system. Based on the findings, I propose 6 recommendations. First, Swap Asia should retain the current DSB planning process in the short term because it provides stronger service protection. Second, SKU-specific safety stock analysis should be used as a decision support review layer. It should help planners identify SKUs that may need review rather than automatically replacing planner judgment. Third, service protection should be differentiated by SKU importance. High contribution SKUs may justify stronger service protection, while lower contribution SKUs may be suitable for tighter inventory control. Fourth, forecast accuracy should be monitored by forecast horizon, because longer horizon forecasts showing higher error. Fifth, planning reports should separate warehouse stock on hand, purchase orders, and planned orders. These represent different levels of supply certainty. Finally, cost assumptions should be refined using internal financial data such as carrying cost, markdown cost, obsolescence cost, and lost sales cost. The key message is targeted review, not mathematic inventory reduction. This project connects statistical training with a real organizational planning problem. From the statistical side, the project applied data cleaning and panel construction, forecast error measurement, ABC classification, safety stock modeling, train test backtesting, and cost sensitivity analysis. From the industry side, the project showed how a business problem can be translated into measurable statistical questions. Instead of asking only whether inventory is high or low, the project measured service, shortage, cost, and policy performance. It also showed the importance of communicating assumptions clearly. For example, the project openly states that actual sales are a demand proxy and that the analysis is not a full inventory transaction simulation. In terms of report preparation, the written report was structured according to the Industrial Statistical Project guideline. It includes project directions, analytical framework, methodology, findings, discussion, recommendations, reference, and appendices. Overall, the project helped connect a statistical method with practical design decision making in an industry setting. To conclude, inventory policy should be reviewed through both service and cost. The observed current planning baseline should not be replaced directly. It achieved the strongest service protection and the lowest total cost under the baseline assumption. Policy C is the best statistical alternative, but its practical value is as a review layer rather than a direct replacement. The most appropriate path is gradual improvement. SWAP should preserve the service strengths of the current planning process while using SKU levels statistical evidence to identify targeted inventory review opportunities. So, the final message is gradual improvement, not directly replacement. The project shows that the DSB data can be transformed into useful decision evidence and that inventory planning can be improved through better cost visibility, service prediction, and SKU level review. Thank you.